I'm Professor Carl Thompson. I'm a professor in the Material Science and Engineering Department, and also the director of a new laboratory at MIT called the Materials Research Laboratory. I was academically trained in material science and engineering and also applied physics. And the research I did was sort of fundamental, sort of abstract. But I came to MIT to work in the Research Laboratory of Electronics as a postdoc. And there I learned that many of the things I was very interested in academically and good at were things that were very important in the electronics industry. And that sort of was transformative for me. And I joined the faculty at MIT, and over my career I focused on the sorts of problems I was good at that were also relevant in microelectronics. And that evolved to microelectromechanical systems and devices and electronic devices, but also circuits, always from a materials point of view, not so much from the device point of view, except how you make the device and how it performs and how you design the materials and make the materials in such a way that it performs the way you want it to. But also what limits the reliability of a device. Any device or system ultimately wears out, and that became an important theme in my research, is trying to understand how and why that happened and how to fix it to the extent we could. So one example, again in the reliability area, and a system level example, the system being integrated circuits, microelectronic systems, is understanding, as I mentioned earlier, what affects how long the system can work, and that depends on the materials very strongly. And in the case of integrated circuits, I particularly focused for quite a while on the wires that integrate the devices or connect the devices. And a modern high-performance integrated circuit, which is about 4 square centimeters, you have literally billions of electronic devices. And you have to connect those devices with wires, and at least 2 wires, usually 3, sometimes more wires. And so in this integrated circuit with billions of devices, you have very tiny wires made using microfabrication techniques like lithography. And they're in the dimensions of a few tens of nanometers. They're made of a material, copper, that can diffuse out and affect the circuit very badly. And so you have to have a barrier around those wires that prevents diffusion, and that's in the range of a few nanometers or less in thickness. And if you took all the wiring in an integrated circuit and you could connect it and stretch it out, it would be about 20 kilometers in the highest performance integrated circuit. And it's wires with dimensions of tens of nanometers with these coatings that are a few nanometers thick, and it all has to work, and it has to work for years, okay? And so, of course, that really is strongly dependent on how the material is made. And how it is made affects things like the crystal size. Almost all metals that are used in applications are made of many small crystals called grains. And one of the things I've been very interested in is what controls the size of those grains when you make the material, and then when you process it to make it into these wires, for example, how that grain structure evolves. And in this particular case, that's really important because the grain structure affects processes that ultimately will lead to failure of the circuit. Stresses can lead to failure by one of the lines breaking or developing a void, a hole. There's a phenomenon called electromigration, where this electron wind, going through the wires at enormous current densities, starts pushing the atoms around, and that can lead to extrusions of metal and the formation of holes that lead to open circuit failures. The rate of that depends extremely strongly on the grain size and how the grains are oriented relative to the current directions. And that's something we knew how to control. And orienting the crystals so that they they only met, the different crystals only met at boundaries that were aligned along the length of these wires, improved the reliability tremendously, by orders of magnitude. And it's because this process of electromigration occurs much faster at the boundaries between crystals than it does if it has to go through a crystal. And that's just one example. I've also worked on this process of forming the crystals, and how they come together has a big effect on the stress in films. Huge effect. The stress in a thin film can be, as you've made it, as you've deposited it, the stress can be of order gigapascals. That's a huge stress. That's the sort of stress that would almost certainly cause failure in a large device or material. Those sorts of stresses are hugely important in microelectromechanical devices and systems, where you use not only the electrical properties but also the mechanical properties. And if you have a very high stress in one of the materials that's used in these mechanical devices, then that can cause the film to, first of all, it can cause it to curl up or fall off. Or if that doesn't happen, it can control the properties tremendously, how hard you have to pull on it for it to move, or whether or not it buckles, which is usually a huge problem. And so we worked on something that was exciting to me academically, but was also very important in this set of applications.